A word from this video sponsor. Got an idea for a circuit, widget, or device that you want to rapid prototype or sell? Check out JLC PCB. They offer their board manufacturing services starting at $2 for 5 boards and only take a few days from start to finish. So make sure to check out JLC PCB, and once again, thanks for making this video possible. Now let's get on with the video. Hey there YouTube, this is SJM4306 back with another video. Just a quick update. My old soldering iron tip burned out. Used this guy for about like 10 years or something. And this is on my Radio Shack, like digital temp controlled iron. You can just about see it in the corner there. So I bought a replacement tip for this. So hopefully this lasts at least another 10 years as well. And I'm going to see about getting more replacement tips because apparently this iron uses like a non-standard wiring for this. So if it dies again in 10 years and there's no replacements available, I will be very sad. Anyway, ordered some very interesting Numitron tubes, and I've done a video before. Let me see if I can find where I put it. Here we go. I've done a video before about a tiny little desk clock that I made using these aircraft Numitron tubes from 1974. And so I did a video on that, and I really like the Numitron technology. It's really neat. So I ordered some more tubes, and these are IV-16. And you can see here they were manufactured first month of 82. I guess first month or first week, maybe January or earlier in 1982. So these are not as old, but they're still really cool. They're 7-segment displays. They're basically 7 incandescent little filament type light bulbs all in the same package. And the filaments themselves are arranged in such a way that they form a 7-segment pattern. And so these guys were not too expensive. I think they were like 20 or 30 bucks, something like that. They are shipped from like Russia or Ukraine or somewhere, you know, in Eastern Europe they were shipped from. So they did take quite a while to arrive. And I just ordered some prototype PCBs from JLC PCB, and this actually, interestingly enough, came in a blue box. I've never seen them ship in a blue box before. So let's just see what we have here. I can already see something I like. They shipped a really cute little, I guess that's like a beer of some type, keychain. That's really cool. Okay, more important than that is the actual boards themselves. And here we go. Let me just set this aside. And we're going to cut this open and see how the boards turned out. They're pretty tiny. Okay, here are the boards. And hopefully I got the footprint right. I couldn't find any footprints available online, so I had to make my own. So in terms of width, it looks about right. Hopefully I left them enough spacing. I opted for the gold plating on this. You can hopefully see it's all kind of goldish, and it's beautiful. Even my logo I did kind of like cut out from the solder mask so that it would be the exposed shiny metal underneath. That looks fantastic. Now I did put spots for a vertical riser board, and hopefully that works out. I'm not sure. So my idea was to have like colons made from tiny little wheat style LED, or not LEDs, incandescent bulbs, and they would mount on vertical boards. So I've yet to design the vertical board. That'll be the next step. But first I need to verify that all this will work. So anyway, I guess what I'm going to do is start assembling this and probably do a quick test after I've soldered the first one, just in case it doesn't work. This is pretty simple. These are low voltage devices. They're just light bulbs, so they can run off of like 3 to 5 volts-ish. So I just have them run off of a bunch of chained 74HC 595s, basically shift registers. And if you set the bit high, they light up. If you don't, they shouldn't. So anyway, and these are all, they all have a common pin, which is the first pin on them. So anyway, yeah, let's get about assembling this. I'll probably maybe show you guys assembling one digit, and I'll do all the rest off camera since it's very repetitive. Okay, one little gotcha. I just inserted the first tube. Luckily, I did make the holes large enough this time. In the past, I've made a couple of mistakes where a few times I've made the holes just barely larger than the leads, and it's really hard to insert them. This time it's pretty good. I could probably have stood to made them a bit larger, but it does fit well. And I'm not going to put them right up against the board just because the glass and the metal might have different thermal expansion. And I don't want to accidentally, if it gets too cold or too warm, crack the tubes. So I'm going to have them stood off just a tiny bit each one. And aligning the tubes themselves will be important so that they're not all higgledy-piggledy. But one thing that I just thought about is before I actually solder this, I think I want to solder all the surface mount components. Once I put the tubes in, it'll be really difficult getting in there. Sort of, yeah, and the board can't really lay flat by that point. So anyway, I'm just going to do the surface mount components first, and then do the tubes. And a first for my channel, I'm actually going to try out this Kester flux pen. And I've always used kind of syringe type flux, whether liquid or gel. So I've never tried these pens. They're cheap, and I thought I'd give it a try. It should be less messy. This is supposed to be no clean, or as I say, less clean, because it's liquid type. It should be quite a bit easier to clean off, not quite as sticky. So anyway, let's fire up the iron. And I don't think I'm going to break out the microscope for this one. So I'm just going to try to do this by hand. So I'm just going to go over. See, is that even depositing? Yeah, there we go. So you need to kind of push on it, the tip, I guess, because this is a brand new flux pen. So just going to get a tiny little bit of solder. And just maybe pick this corner pad there. Tweezers. Grab one of these chips. Make sure the orientation is correct, obviously. And we are just going to tack down the corner there. So let's see. Make sure we have this side aligned correctly. Grab the other corner. Let me just manually inspect. Looks okay on alignment, just maybe a little bit. This isn't a very densely populated chip, so it's not super critical. The alignment. And one thing I'm noticing on this flux pen is maybe I need to actually kind of use more of it, since it doesn't seem to really be super active. I'm not really liking this flux pen so much so far. It's not really doing its job. It looks like joints are kind of meh, so I might switch. There. Yeah, I think this pen maybe I have to, practice a little more with it or something, but it just doesn't seem to be as good as the gel flux that I normally use. The gel just applied via syringe just flows much better. Or maybe I need to actually dab this on a lot heavier because it's not quite as reactive or whatever. But yeah, anyway, first chip done. I'm just going to go through and I guess solder the rest of them and then proceed to the tubes. Okay, just finished soldering the SMT parts, and this flex pen actually works pretty well. I had to actually push it several times and kind of give it a shake. I suppose it like the tip is sealed or something, and it when you first get it, and you had to kind of like push it down to break that seal so that the liquid comes out. Once the liquid did come out, it soldered just right, so that works well enough. So I'm definitely gonna probably use that more than the gel. The gel is kind of, it's good for certain things when you want to stick a part down, but it's just super messy and it's really hard to clean. So yeah, you can see the soldering is all done for the surface mount components. Now we just got to do the tubes. So gonna have to figure out a process of doing that um, while keeping everything aligned and not damaging the tubes or anything. Okay, so I wrote up some demo code right over here. Basically, I took the software serial function that I wrote for the DL1414 display, and I copied and pasted it, and I changed it just to have only one digit. Ignore that comment. And so anyway, what I'm actually doing is I'm using a lookup table to store the patterns for each of the digits 0 through 9. And as you can see, I have a count value, and every time it goes through this loop, it increments a count as long as it's less than 10. And you can see it running right here. And this is actually very sharp. Yeah, there we go. Get it in focus. And there's only one digit soldered. I just want to make sure that my circuit was correct. I didn't mess up the routing or anything. So now that I'm sure that this works, and this actually looks really cool too, now that I got this first test out of the way, I'm just going to go ahead and solder the other digits, and then I have to modify the library to support all 6 digits and the decimal points when I get to that point. But anyway, yeah, works so far, and just powered off of 5 volts. And the output enable pin on the shift registers is PWMable, so I should be able to actually adjust the brightness in 256 steps. So that'll be neat. And here I modify the code to PWM the output enable on the shift register, and as you can see, it's getting brighter and dimmer. And unfortunately, I was actually going to do per digit controllable PWM, but I decided that would just use too many I/O and it'd be kind of more of a pain, not really that useful. So I just tied all the PWM pins together. So whatever brightness you set, all the digits will have that brightness. Yeah, you can see there. Works. Okay, so here is the finished, fully soldered board. And yeah, so each tube gets its own shift register, and I've updated the code to support all the digits, and I just have a simple counting program on it, and it'll go through, and this last digit is sort of the reference for the fastest rate you can update this. Because it's incandescent, there is some like afterglow on the segments after you turn it off, and it takes a little bit for it to turn on as well. So it's not like an LED display where it just instantly turns on and off. So multiplexing these might be kind of a little bit difficult. Well, yes and no. It might actually help you that there's some like latency, because it'll give a smoother update at like a lower frequency. But anyway, you can see that it does work, and updating like once per second works just fine. So I can have these as a seconds count. So yeah, my idea is to make a clock. These will be hours, minutes, seconds, and then I'll have colons. And for the colons, I'm actually going to use these tiny, oops, where did it go? Oh, tiny grain of wheat style bulbs. And I forget where I pulled this from. They're pretty cheap. You can buy like a bag of 100 of them for like a couple dollars on eBay. So I'm going to use those. And those will be on a vertical riser board. That's why I left little slots and little solder pads. So I'm going to design a vertical board that goes in there that'll hold 2 of those. And each one actually will be independently, each colon will be independently controllable. So there'll be 4 extra little dots. And those will be for the colons, obviously. And I can use those as indication or just flash them every second or whatever I want to do with them. they will be independently controllable. But anyway, yeah, you can see everything works. It's just counting and incrementing, and it looks actually a lot clearer in real life. Here, it sort of looks drowned out because the tube surface is reflective, so you're seeing a lot of like streaking from ambient light. But to my eyes, it actually looks super clear, and in the dark, it looks fantastic. It's really hard to capture on camera though. It kind of washes out the camera sensor. But yeah, it just has like a really nice warm glow. Now, all these tubes being on at once, this is just powered off of a USB, like a phone charger. The chips actually get slightly warm, and I don't think it's going to be a problem. They don't get hot or anything. I've left this running for like 10 or 20 minutes continuous, and they just reach like a warmish temperature and then stop increasing. And the tubes themselves, obviously they're filament based, so they are going to get a little bit warm. The good thing about these types of incandescent displays, unlike an LED, which will draw as much current as possible and then burn itself out if you don't limit the current in some way, these displays will actually, they're kind of self-limiting. Basically, as the filament warms up, the resistance in the filament increases, and it'll eventually reach a point where it stabilizes, where it won't draw any more current and it won't get any brighter. And so you actually don't need resistors or anything. I just put diodes, just because in a past clock that I made, I use a similar topology, and I get bleed through between digits, even though they're not multiplex, which is really odd. So I just added placeholders for diodes, and that drops the voltage just a little bit. Okay, while that's going, a little bit of technical information. So I drew out the pinouts for this tube, and this is looking from the bottom of the tube. The front is here, and pin 1 is the common. So basically how it works is you hook common up to either positive or ground. Pin 2 is not connected. And pins 3 through 9 are each of the segments as follows. So I label it A, B, C, D, E, F, and then G is the center part. And so basically you just hook up voltage to any 2 or more of these. Common always has to be powered, obviously. And whatever segment you hook up to the other power pin will light up. And that's really simple because these are just incandescent bulbs. And so the circuitry for the driver section of this is actually pretty simple. Basically, we have, this will be a 595. These are serial shift registers, so they only have 3 pins each, and then an output enable, which you could just permanently tie low to turn it on, or you can PWM to change the brightness. And so there's a latch, a clock, and the data. That just so happens to be LCD. Anyway, and these are all shared amongst all the displays. They're all in parallel. This will be another 595, and then that just repeats over and over again. And each of these, there's actually 8. I'm not going to count, whatever. There's 8 wires going over. This is the actual display itself. There's a little 7-segment drawing there. So yeah, so that's generally how it works. And between all these displays, the common pin is actually tied. I believe I had it to ground. And so when you set the data high on the pin, that segment will light up. And in between, I do have a diode for each display. But actually, that's not strictly necessary. I just added that because I'm paranoid. But yeah, so other than that, it just repeats over and over again. And so I have this 6 times, but this could easily be expanded to have 8 digits, 16 digits, whatever. You would just have a lot of bits to shift in. So per digit, you have to shift in 8 bits to each shift register. And so say in this example, I shift in 16 digits, I actually have to reverse the order because the oldest digit gets sent out the earliest, so it ends up at the end of the line. And so in this example, if I send 16 bits, the first 8 will go in here and the last 8 will go in here. And that's basically it. There's really nothing that special going on here. It's just a matter of sending out the data. And because shift registers have memory, they store the data, you can just send the data, and if you don't change it, it'll continue being displayed on the tube itself. Now, in order to like do some sort of animation or something like that, you will have to kind of buffer the display, because in order to change this digit, you have to shift in all the previous digit datas. And if you change any of them or clear any of them, it'll stop displaying what it was previously displaying, obviously. So there is a little bit of data manipulation to get things to line up correctly so that it displays what you want it to display. But overall, shift registers are actually really cool, and they're really flexible, and they're cheap too. I think I got like a bag of like 50 of these for only a couple dollars, like $2 or $3. And so I always keep a bunch of shift registers around because they're really easy to use, and they're actually really fast. I've driven these up to like 5 or 10 megahertz, no problem. And really cool that you can PWM all of them using the output enable or disable it. If you're getting like ghosting between the digits, you can disable them so that when they're updating, they don't display anything. A really neat trick to do is if you give it a very slow SPI clock and you leave the digits enabled, you can actually see the data shifting, and it just like goes through each of the tubes. You can actually see it, which is really cool. That's a neat thing to do that demonstrates exactly how SPI shift registers work. But anyway, yeah, you can see they're very clearly visible, and it just looks absolutely fantastic. And the viewing angle's like really wide too, obviously, because it's just an incandescent filament. So, and they're sort of three-dimensional too. You can see they're standing off of the background. But yeah, I absolutely love this. Works perfectly. I really like the black solder mask on like different display boards. It works really well. This is matte. Actually, at first I liked the glossy, but I think the matte's growing on me. And the white silk screen stands out really well from it. And other than that, I put some mounting holes, but they're kind of too close to the tubes. I didn't really account for that. So these front ones I probably can't put screws in, but this back one even is a little close to that chip. So pretty much, this is light enough though. I think I can mount it off of this right angle, or this vertical pin header. I can just solder that into the controller board. So I'm going to design a controller board that's the exact same size underneath, and that's going to contain the real-time clock. And I've been using the same real-time clock chip, the DS1302, for all my projects. I actually upgraded. I found a I2C real-time clock chip that uses MEMS oscillator. So it's like 2 to 3 times, well, it's, I think, I want to say like 5 or 4 parts per million in terms of like the accuracy. So it should actually only gain or lose, like, it's ridiculous, like under a minute a year, which is crazy. So it's much more accurate than the real-time clock that I usually use. And it's in the same package, SOIC 8-pin package, and requires no crystal. The only gotcha is it doesn't do the battery backup charging on its own. So we'll have to put, an extra diode and a resistor. But that's no big deal. It will be more accurate. So my idea is I'm probably going to have Bluetooth so you can connect to it on your phone and change settings and set the time. Because this only has numbers, I tried making a simple menu system on my Nixie clock that has like the same number of digits, where it'll have the setting mode will be numbered like 1 through 5. for whatever setting. But the problem with that is you have to memorize what each number means, which is really annoying. So I'm just going to have this, you connect to it over Bluetooth, and the menu will actually come up over ASCII basically on your phone, and you can manually set everything using like AT style commands. I think that'll be a lot easier and a lot more future proof. And of course, I'll have buttons to hard set the time in case you don't want to pull out your phone, so you can change it that way. But yeah, so I'm thinking of adding quite a number of new features to this clock, and it's really tiny, and I really like how cool it looks too. One thing that stinks is all these digits are like the same height. This one digit I didn't notice. The manufacturer, I believe they made these by hand, and so it's slightly higher on this one digit right here. And it's not even the tubes higher. The actual display board is shifted upwards inside the tube, and it drives me nuts. Just like it's slightly higher, but it's definitely noticeable. So that's really annoying, but I can live with that. Aligning all the tubes actually wasn't that hard. I was just really careful. Soldered one pin and then gently like shifted it so that it's parallel with all the other tubes, and I did an okay job of that. But yeah, anyway, hopefully you guys enjoyed this video, and this is just the first part. Second part, I'm going to design that little riser board for the colons and then the actual clock board itself, so stay tuned for that. And once again, thanks for JLC PCB for providing these PCBs really quick too. I ordered these like, must have been like last Friday, and they're already here. It's well, I got them yesterday, so it took about a week, including shipping. It only took like 3 days to manufacture, and then the rest was shipping via DHL. So I got them pretty quick, actually, within a week. And yeah, so anyway, hopefully you guys enjoyed this video, and I will see you in the next one. Bye.